Hi everybody, we're going to start talking about section 4.1, which is extreme values of functions, which is just another way that we describe maximums and minimums. And so let's talk right now the difference between an absolute max and min and a local max or min. What absolute just means is that it's either the absolute highest or the absolute lowest part of the function. I have circled right now the two absolutes. We have the absolute maximum up here, which basically means that the function, no other point on the function is higher. And then we have an absolute minimum, which in this case occurs at an endpoint. This is a closed interval. You need to kind of imagine that there are closed circles on the ends there. And so I have an absolute minimum out here at the endpoint because there is no place on this function that is any lower than that point. As well as absolutes, we also have local min and maxes. Okay, and a local just means that he is a maximum in his own area. So right here would be a local maximum. Okay, and there are no other local maximums except you could call this a local max. Any kind of absolutes are also locals. Okay, but the and then we have a local minimum here at x equals e. And we also have a local minimum at this endpoint out here, x equals b. So they're not the absolute lowest, but they are just the lowest in their neighborhood. Okay. We're going to talk right now about the extreme value theorem. And what this means is that if you have a function that is on a closed interval, and in this case our closed interval is over a to b, and f your function is closed, then you are guaranteed to have both a maximum and a minimum, meaning absolutes here. And so I want you to look at all four of these pictures, and every one of these endpoints are closed. If they were open, we could not say that the extreme value theorem applies. That is a hypothesis that needs to be met in terms of the extreme value theorem. You can see here that in this first example right there, we have a local max, or I'm sorry, an absolute max at x sub 2, and we have an absolute min at x sub 1. On this example right here, we have an absolute maximum at the endpoint at x equals a, and then we have an absolute minimum at x equals b. In the lower left-hand picture, we have an absolute max up here at x sub 2, and then an absolute min at x equals a. And then we also have in the lower right-hand picture an absolute min at x equals 1, or at x sub 1, and then we have an absolute maximum at x equals b. Okay? So let's talk about local extreme values. I think this is something that just kind of makes sense, but we're just going to put the definition out there for you. It says if a function has a local maximum value or a local minimum value, okay, at an interior point, an inside point of C in its domain, and if the derivative does in fact exist at that place, then the derivative must equal 0. And what this means right here is that the slope has to equal 0. Well, that makes sense. If you have a local min at this point down here, it should follow that if I put a horizontal tangent line in there, or a tangent line, it would be horizontal. And it would be the same if I have a local max. Okay, that tangent line would end up being 0, meaning the derivative would end up being 0. Okay? And we also need to discuss critical points and why they are so wonderful. A point in the interior of the domain of a function, f, for which the derivative equals 0 or the derivative does not exist, those are called critical points. So a critical point basically here is where your derivative is equal to 0 or where your derivative does not exist. Okay? Here's the moral of the story, folks. Any function that has extrema, the only place that the extrema is going to occur is going to be at an endpoint, if it's available, or at a critical point, where the derivative is 0 or undefined. These are going to be the only places that we care about to even find maxes or mins. They have to occur at either endpoints or critical points. Okay, let's do a couple examples. This first example here says, let's find the absolute extrema. We're going to find the absolute max and the absolute min of this function, f of x equals 3x to the 2/3 on the interval, on the closed interval, if you can tell here, these are brackets, from -1 to 2. Okay, now we aren't going to use a calculator here, but we kind of can tell a little bit of information. I know that this 2/3 power is going to create some sort of a cusp or some sort of a vertical tangent. Okay, and I know that because that's what fractional exponents do. Okay, and we can talk a little bit more about that later. We also have endpoints. They were very explicit, and they told us that our endpoint there was -1 and +2. Okay? They aren't always that nice to you. So what we need to do here is figure out first, what are my endpoints? Well, they already told me that. That's nice. So we have an endpoint here of x equals -1. We know that could be a potential place where there's a max or a min, and we also have x equaling 2 as another potential spot that could be a max or a min. We now need to figure out our critical points, because those are the only things we care about, endpoints and critical points. Well, I know endpoints and critical points. In order to find critical points, I need to find the derivative. So let's find the derivative of this guy. Okay, it's a basic little power rule here. We're going to take our 2/3, move it to the front. So 3 times 2/3 is 2, and then x to the, and then I'm going to subtract 1 from my power, so that's going to be to the -1/3. Okay? And so what we need to do here, now that I have my derivative, I'm going to just clean it up just for the sake of making it a little bit more usable and move that negative exponent to the bottom. So we have 2, and then I'm going to go ahead and put it under the third root. And so we have that right there as our first derivative. And I'm going to set that equal to 0. Okay, because a critical point is taking your derivative and setting it equal to 0. When I multiply this cube root of x to the other side, that's going to wipe it out. And I know that 2 cannot ever equal 0. So there is no place where my derivative is equal to 0. Okay? If you remember back on the previous slide, however, critical points are also where your derivative is undefined. And so we have to also look at our denominator here and figure out, where does the denominator equal 0? Okay? Because that's going to be a place where my derivative is undefined. And so if I would want to get rid of that cube root, I would just raise everything to the third power, and x raised to the third power, in this case 0, is still going to equal 0. So I do have this, x equals 0, as a critical point. So I'm going to add him to my list. All right, so I'm going to erase some of this work I have here. All right. So what we're going to do at this point is we're going to make a continuum, okay? Or basically a number line. And I'm going to put all of my endpoints and critical points on that number line. So I have 3 places to check. I have -1, I have 0, and I have +2. Okay? And what I'm going to do is make this a continuum for my derivative. So just make sure you're realizing that the values that I plug back into my function are going to get plugged back into my derivative, okay? Because we want to see where the derivative is positive or negative. So I'm going to pick a value in this range, in this domain right there. So how about we pick -1/2, okay? If I put -1/2 back into my derivative, all I want to do is see if it's a positive or a negative, okay? And so if I do that, I would have 2 over the third root of -1/2, okay? Well, I don't really know what the third root of -1/2 is, except the fact that I know it's negative. And I know that my numerator is a positive, so a +2 divided by a negative is going to end up being a negative. So I'm just going to put a negative in that spot right there to show that any value coming out of that domain from -1 to 0 is going to result in a negative number. Then we want to pick a value somewhere in this group of numbers, that interval. So let's just be easy on ourselves and pick 1. And I'm going to put 1 into my derivative. So I would have 2 over the third root of +1, and that's a lovely positive number. I don't even care what it is, even though I know it's 2. Okay? And so we now know a little bit of information about this function. Okay? We know some information about the slopes of this function, because remember, this was a continuum that gave us some information about the derivative. So if you know that this place over here, let's use green, this place in here a negative slope, that means that my function would have to be falling in that range of values. I don't know the shape of it. I don't know if it's kind of concave up or concave down, but I just know that it's decreasing. And then I know that in that interval from 0 to 2, he's rising. And so you can see that at this point right here at x equals 0, we do in fact have a minimum. Okay? We also know that since it would be closed, we have a maximum at my endpoints. So each of my endpoints are maxes. Okay? We need to figure out the absolutes, however, though. And so I'm not sure if x equals -1 or x equals 2 is a maximum. We need to figure out which one. So we're going to plug -1 and +2 back into my original to see which one is a larger value. Okay? Okay, so let's take -1, and I'm going to put it back into my original. So f of, -1 here would end up being 3 times -1 to the 2/3 power. Okay, and if I want to rewrite that to make that a little bit easier to solve, that would be 3 times the 3rd root of -1 squared, right? If I put that into the into a root. And so -1 squared is +1. A +1 cube rooted is going to also be +1. So the answer here is 3. And so I know that f of -1 is 3. Okay? Let's see what's going on at 2. So if I put f of 2 in, let's solve for f of 2. So we have 3 times 2 to the 3/2 power. 2/3 power. Okay, and so that just means 3 times the 3rd root of 2 squared. And so I don't really know what the 3rd root of 4 is, but I do at least know that it's larger than 3. Okay, so f of 2 is just going to, we're just going to leave it as 3 times the 3rd root of 4, and know then that this guy is bigger than this guy. Okay? And then we also know that at x equals 0 we have a min. So let's just figure out what f of 0 is. Well, that's pretty nice. F of 0 would end up being 0. Okay? And so this guy right here would result in an absolute min. And this guy right here would result in an absolute max. And then this guy right here would just be a local max. Okay? Not too bad, is it? Let's do one more example together. Okay? We're going to find the extreme values of the function 1 over the square root of 9 minus x squared. And notice in this example, they did not explicitly state any domain. They did not give you any endpoints. And so we have to kind of look at this and figure out, would I even have endpoints? Okay? And the best way to tell that is to just find your domain. And let's see what the domain of f of x is. Well, I have a square root on the bottom. Okay, and I know that I can't have a 0 on the bottom. And so if you remember to find domains of these guys, you take your inside and you set it greater than 0, only greater than because it's on the bottom. Okay, and so if I would do that, I'm going to take my 9 minus my x squared, set it greater than 0, and I'm going to solve it for x. So I'm going to subtract my 9 over. That will give me negative x squared is greater than negative 9. And then I'm going to divide my negative off, which would then flip my sign. And then I'm going to square root both sides. Now, if you remember, square rooting both sides is going to generate two answers, x equals 3 and x equals -3. And in the world of inequalities, the positive guy keeps the symbol, and then the negative guy gets the opposite symbol. And so our domain in this case does not have any endpoints. And so we do not have any endpoints to worry about. Okay? Solely because its only domain is between -3 and 3. Okay? With that being said, we need to find critical points. And critical points, remember, are where your derivative is 0 and also where your derivative is undefined. Okay, and so I'm going to find my derivative here. So the derivative of f of x, if you remember up here, this guy I could rewrite as 9 minus x squared raised to the negative 1/2 because he's in the denominator. And so I'm going to pull that negative 1/2 to the front. I have 9 minus x squared, and then I got to take one off. Now remember, that would be minus 3/2 in that case. Okay? And so if I were to rewrite this, oh, I'm sorry, and I did this in my example too when I was working these out beforehand. I forgot to chain on my negative 2x. It's like the cardinal sin, isn't it? Good grief. All right, and so now let's clean this up because it's not really very usable. So my 2's here would cancel, my negatives would cancel, and so when I do have this all cleaned up, my derivative would be x on the top, and then I have the square root of 9 minus x squared all cubed in the bottom. Okay? So we need to figure out where he equals 0. So I'm going to set that equal to 0, and my denominator, when it multiplies over, wipes out, and you see that x equals 0 is a critical point. So we do have a critical point to add to our list, x equals 0. Okay? We also have to look at where my derivative is undefined. Okay? So we got to take our derivative here and figure out where he would be undefined. In that case, I'm going to take my denominator, which is the square root of the quantity 9 minus x squared all cubed, and I'm going to set that equal to 0. And so when I square both sides, I'll still get 0. When I cube root both sides, I'll still get 0. You should be okay with the fact of me jumping to this point. Okay? When I solve this, x will equal plus or minus 3. Well, if you remember, plus or minus 3 isn't even in our domain, so it cannot be critical points that we pick to check. So the only thing we have to worry about here, folks, is our one critical point. Okay? So we're going to, again here, make our number line, and we're going to put our lonely little x equals 0 on our number line, and we're going to plug values back into my derivative to figure out what's going on with the slopes. Okay, and I erased my cleaned up version. What was that? We had x over the third root. No, it was the square root, wasn't it? The square root of 9 minus x squared cubed. All right, sorry about that. And so if I put, let's just put a negative 1 in. If I put negative 1 in, my top is going to be negative. My bottom, when I take 9 minus a positive 1, will be positive. And so my bottom will be positive. A negative divided by a positive is in fact a negative. So everything in that group is going to be negative. And so you know that your original function is going to be falling or decreasing. Okay? And then if I pick a positive 1, that would end up being a positive divided by a positive, and so everything in that group will be positive, and so you can see that my derivative in this point would be rising. Okay? And so you can tell that at x equals 0, we have a max. Oh, sorry, a min. Goodness. All right, so we have a min. Let's actually figure out what that value is. So I'm just going to put 0 back into my function. F of 0 is 1 over the square root of 9 minus 0. And in that case, we have 1/3. And so f of 0 equals 1/3 would be our maximum value. All right, this video took a little longer than I was hoping, but I hope it makes sense to you. We will do a lot more of these examples in class, and I hope you have a great day, and we'll talk to you later. Bye, everybody.